The full density matrix of the combined system, the system S and the environment E, is equal to the outer product of the total state vector with itself. In other words, to get the density matrix for the whole system and its environment, you take the state that describes both together and combine it with itself to show all the possible probabilities and relationships within that state. Now form the reduced density matrix for the system by tracing out the environment. We start with the combined system, the system we care about and its surrounding environment. To find the density matrix that describes only the system, we mathematically remove, or trace out, the environment's part. This process is called taking the partial trace over the environment. When we do this, we get an expression that tells us what's happening inside the system alone. The first part gives the chance that the system is in its first possible state. The second part gives the chance that the system is in its second possible state. The last two parts describe how much those two states are still connected, or in phase, with each other. In other words, how much quantum interference or coherence remains. Those last terms depend on how similar the environment's two possible states are. If the environment changes in such a way that those two environment states become very different, their overlap becomes smaller. That means the connection between the two system states fades away, a process called decoherence. So, in plain terms, the reduced density matrix for the system shows both the probabilities of the system being in each state and how much those states remain quantum mechanically linked. As the environment interacts with the system and the environment's states drift apart, the link weakens and the system starts to behave more classically. Key point: the off-diagonal coherence term is multiplied by the environment overlap, bra E1 of t, ket E0 of t. As the environment records which branch happened, the environment states rapidly become orthogonal. Bra E1 of t, ket E0 of t goes to 0. Thus, decoherence goes to off-diagonals go to 0. The reduced state becomes diagonal in the pointer basis, a classical mixture, which means the appearance of distinct branches. That's the mathematical demonstration that branches stop interfering.